every day, to predict weather, to tell time, to handle money. Math is more than formulas and equations. It's logic. Math is more than formulas and equations. It's rationality. It's using your mind to solve the biggest mysteries we know.
Welcome back, Algebra 1 students. Here we are at the very end of Chapter 8, comparing rational or linear, exponential, and quadratic functions in 8.6. And before we get into that, let's take a look at our cartoons, Calvin and Hobbes. Calvin and Susie are walking along the sidewalk. You have your line memorized for the nutrition play, Calvin? I'm still learning it. Being an onion is a difficult role, you know. What are you? I'm fat. No, I mean in the play. And she clobbers him. Anyone else want to say it? It's understudy. I guess Calvin just couldn't resist. All right, moving into our core concept, page 272. You have the three functions there. We can see the linear, exponential, and quadratic. We should be familiar with these by now. Y equals mx plus b, or line for linear. You have your kind of rocket ship, Superman graph, where x is the exponent position, base exponent. And then you've got your quadratic function. This is standard form. Your U shape is your quadratic. So what we're doing here is we're going to be starting, and the first thing is just plotting points to tell whether the points would represent a linear, exponential, or quadratic function. So very simple. Let's just plot. If we were plotting these points, it would plot out like this, and you could see how, yep, that looks like it's going to be a quadratic function right there, because they plot out and they connect together as a U shape. These points here all plot out, and they would be connected together by a straight line, so that's a linear. And if we did just plot these points are connected together like this rocket ship going up, and so that's definitely exponential. All right, so for 1 through 4 on the extra practice, I'm going to have you do that on your own. Just plot the points of each one and tell whether it represents a linear, exponential, or quadratic function. For number 2 and 3, just make sure your y-axis, the boxes there, are going to go up by 2s on just those ones right there. Everything else should go by 1s. All right, so go ahead and pause the video and do 1 through 4. All right, so you should have paused the video. You should have 1 through 4 done. Number 1, if you plot the points, they look like this. That is definitely a quadratic function. As you can see, the U shape. On number 2, with this y-axis going by 2s here, they plots out like this. So it's just going up like that. So it's definitely an exponential function. And then number 3, plotting these points, it'll come down more like this. It's still exponential. Even though these ones look a little bit different, this one's going up from left to right, this one's coming down from left to right. Still exponential functions. And then number 4, plotting these are all straight line, all lined up into a straight line. So that's definitely a linear function. So these exponential ones, you'd have exponential growth. We could say this is actually exponential growth on this one. And you could say this is exponential decay. You might want to write that down for 2 and 3. 2 would be exponential growth, and 3 would be exponential decay. So our joke of the day, why are frogs so happy? So why are frogs so happy? Those little green creatures. Well, because they eat whatever bugs them. There you go. Look at that. Never would have thought. They eat whatever bugs them. Because they eat bugs, of course, you know. All right, moving into the core concept, differences and ratios of functions. This is the way we could figure out whether the linear, exponential, or quadratic, just without the graphs. We're going to be looking at these things called first differences and second differences. And this goes a lot along the way there, especially the differences and the ratios are connecting with what you've already learned with arithmetic sequences and geometric sequences. Linear functions are like arithmetic sequences. Exponentials are like geometric sequences. So the linear function has a common difference. The exponential is going to have a common ratio. The quadratic is going to have a common second difference. Okay, so that's the thing about quadratics. If it doesn't have a common first difference, then you can check it again to see if it has a common second difference for it to be a quadratic. And in all cases, it says the differences of the x values need to be constant. So we're going to be just looking at the y values to determine if it's linear, exponential, or quadratic, but what needs to be definitely true is that all our x values are all going to be constant. So you can see here on these three, all the x values are constant on letter A. They're all constant. They're going up by ones. And if you look at the y values, they have a constant common difference there of going down by 3. So that's definitely a linear function with a first difference that's being constant. So they have a common difference, all the y values. This one letter B here has, again, going up by 1s for the x, so that has to be true. It has to be a constant. Now it doesn't have to be 1, it could be going up by 2s. It just has to be constant for x in order for this to work. And this one you can see they're multiplying by 2 every time. That's an exponential function. It has a common ratio, so it's going to be an exponential function. And then for number 3, again, it's going up by 1s, and the first differences are not constant. So what we can do is we can check the differences again and to see if they have a second difference that's constant, and it does. They're going up by 2s on the second difference when you try that again. So that tells you that it's a quadratic function there for that one. When the second difference is constant, then it's a quadratic. All right, so I'm going to have you try number 5 and 6, but we need to make an adjustment to number 6. They made an error, and I figured this out a little earlier, that they made an error on number 6. So what we need to do first is adjust. This should be not 8. This should be not 6, it should be an 8 here. So this should be an 8, and this one should be an 8. So those should be 8s, not 6s. All right, so go ahead and try number 5 and 6. Do the same thing with either looking at the difference of your y values, or if it has a common ratio to determine whether it's a linear, exponential, quadratic. Go ahead and pause the video and see if you can figure it out for 5 and 6, and then you can play it to check your answer. All right, so hopefully you have an answer for 5 and 6. We'll check number 5 here. So our first difference between 7 and 4, that's going down by 3. Then from 4 to 1, we're going down by 3. 1 to -2, also going by down to 3. Looking like we're having a common difference, and we are. So this is definitely a linear function there. And we have what we call the first differences are constant. And then if we do number 6 on this one's going down by 6. This one's then going down by 2. This one's then going up by 2. And then this one's going to be going up by 6 again. And so we can see that does not have the first differences being constant. So it's not linear like the last one was, but we can try it again, see about the difference again now. And so if I try that again, from -6 to -2, that is going up by 4. From -2 to +2, I'm going up by 4. And from +2 to +6, I'm going up by 4. So second differences are constant, so that means that this one is a quadratic function. And we could say there is the second differences are constant. That's why 6 wasn't going to work on that one. They should have changed it to 8. That should have been an 8 on that in order for this to work. All right, so for number 7 and 8, so now we have just instead of the ordered pairs in a table, we just have a list of the ordered pairs, tell whether the data set represent linear, exponential, or quadratic, and then we also want to write the function. So we can do the same thing. We can see the x's, are they all constant? They're all going up by 1s, yep, just like these did here. We can even see this one, same thing. They're all going up by 1s on number 8. So if I just look at my y's now, I'm going up by, from here to here, actually going, up by 3 on that one. From -1 to 2, also going up by 3. From 2 to 5, going up by 3. From 5 to 8, going up by 3. So this is definitely a linear function on this one. So now we need to write that function. So we know it's going to be y equals mx plus b in this format. So the format is going to be, I'll say y equals mx plus b right here. Now what we know is, in this case, we could try to find the m. We could find the m by just finding the slope of 2 points if we want to. But what we are shown here is we are shown the b. b is right here. where this is your y-intercept, 0, 2, and that is always b. So we know what b is, it's 2. We can pick a number for, we can use this point right here, 1, 5, that's some small numbers. And then I can just put in 5 for y is equal to m times x, which is 1, plus b, which is 2. And then just solve for m at this point. And so that's going to give me just 1m, so I'm going to subtract 2 from both sides. So it's going to be 3. So 3 is equal to my m. 1m is 3. So my linear function is going to be this. I could start off with f of x. You could say y equals, but f of x is our function notation. And then it's going to be 3 for m, so 3x, and then plus 2. So that's our answer here for number 7. Number 8, when we want to look at the first differences from 9 to 0, that's going up by 9. 0 to 3, going up by 3. 3 to 0, it's going down by 3. And then 0 to negative 9 is going down by 9. So it doesn't have the first differences. Let's look at second differences. So from 9 to 3, that's going down by 6. 3 to negative 3 is going down by 6. Negative 3 to negative 9 is going down by 6. So that is definitely a quadratic function. So this one is quadratic. And then in order to write the answer for this one, and I'm running out of space here, so actually let me move this up a little bit. So I'm going to move this, I'm going to say the answer down here. This is quadratic. And our answer will be f of x equals, maybe I'll do a different color again for the f of x equals, let's use red down here. So f of x equals. So what we need to remember is we have a couple intercepts here. So when y is 0, here's our intercepts. So our intercepts are right here. This could be what we call the p and q number. P and q. We looked at those when we were graphing quadratics in the intercept form. So our intercept form is like this, like y equals a, and then it's like x minus p and x minus q. That's our intercept form. So those are our p and q numbers. We can plug those in, and we also want to pick a point here. I'm going to pick maybe 0, 3, that point, to plug in for my x and my y. So this will be my x and my y, just like I use 1, 5 for x and y on this one. So y, in this case, is going to be 3. So 3 equals, we don't know what a is, that's what we're trying to figure out. And so we know x from our point is going to be 0. So 0 minus negative 1. Well, that's going to be like 0 plus 1 then. And then 0 minus positive 1 for q. And so we say 3 is equal to, basically a is going to be, this is going to be 1, this is going to be negative 1. So it's really going to be a negative 1a right there. Well, that's going to be 1 here, but this is negative. So 1 times 1 is going to be 1, times a negative is a negative 1 in front of a. And you could multiply both sides by negative 1. That leaves you now with a is equal to, multiplying this by negative 1, it gives you negative 3. So our a is negative 3, so we start off with that, negative 3 times, and then it's x minus 1 and x plus 1. You could have put x plus 1, x minus 1, that doesn't make any difference. But that's our quadratic function right there written out. All right, let's move on to our next one, which is number 9. Before we get to number 9, let's do a little thing here about comparing. So I want to talk about comparing. It says comparing the functions using average rates of change. You see that on page 272 or 73 up there at the top. Over the same interval, the average rate of change of a function increasing quadratically eventually exceeds the average rate of change of a function increasing linearly. So basically, the quadratic is eventually going to overtake the growth of a linear. So the value of a quadratic function eventually exceeds the value of a linear function. Okay, so that we should understand. The quadratic eventually is going to grow faster over time than a linear function will. Linear is going to grow slower. On this one, it says over the same interval, an average rate of change of a function increasing exponentially, or exponent one, eventually exceeds the average rate of change of a function increasing linearly or quadratically. So the value of the exponential function eventually exceeds the value of the linear and the quadratic. So eventually the exponential is going to overtake the quadratic and the linear in its growth. This one eventually is going to be growing a whole lot faster. And so it's going to get a lot higher. As you notice, this one we know is like the rocket ship taking off. It almost seems, though, at first that it's not growing as fast, but eventually it does take off. So I wanted to kind of go over this just with these three examples. So if we look at just plugging one in, so I have a linear, just y equals x, quadratic y equals x squared, exponential 1.1x. I had to put a base here. So to try to get it as close to 1 as possible, I just put 1.1 so we can kind of use that. So if x is 1, we know for the first one right here, it's just going to be y, the output would be 1. So y is 1. Okay, so that's as far as it goes. On the y, how high is it going? It's going up 1. 1 here, y, or 1 squared is also 1. So y is equal to 1. It's the same. Linear and quadratic are the same when x equals 1. Okay, so it looks like they're the same. Right here, if you put 1 in here, 1.1 to the first power is just 1.1. So y is equal to 1.1. So just by plugging 1 in, you're all about the same spot with all three functions. But now let's make the x grow a little more. Now think of it as time, like let's say 1 day, 10 days, 100 days. And you can think of it in terms of money if you like to do that. Like if you have a savings account and a linear savings account, a quadratic savings account, and an exponential one. And there's 1 day of saving the money, 10 days of saving the money, and 100 days in saving the money. So if you say, okay, after 10 days, and plug in 10 here, if you have 10, you're going to get 10. Okay? And in this one, if you plug in 10, 10 times 10, you'll now have 100. If you think of this as dollars, okay? So after 1 day, we have $1. After 1 day here, we have $1. After 1 day here, we have about $1. After 10 days, we have $10 in linear. After 10 days, we have $100 in the quadratic. After 10 days, now here's where I'm going to have to use a calculator. Let me bring this up. So it's going to be 1.1, and then we're going to raise it up here to the 10th power, and equals 2.59. So y is equal to 2.59. All right, so it didn't look like the exponential one went up so much. After 10 days, we got $2.59. Okay, not so great there with exponential. But we see that over the interval here of just 1 to 10, the quadratic has definitely overtaken the linear. All right, so now let's go for an interval between 1 and 100. So if you plug in 100 here, you're going to get 100. So after 100 days, you have in the linear account $100. Here in the quadratic, it'd be 100 times 100, which is going to be 10,000. And this one you would have after 100 days, you have $10,000. And then the exponential one, let's use the calculator again. Pull this up. And so after 1, we're going to 1.1, and now we're going to raise it up to 100th power. So the 100th power equals. And now look at this one. Remember how when we were at 10, it was at $2.59? Well, now at day 100, oops, I lost it there. At day 100, we're at $13,780 with like 61 cents. I won't put the cents down, but 13,780. So y is equal to 13,780. So the exponential one at this point, in this interval between 1 and 100 days, the exponential has now overtaken the quadratic and the linear, as you can see. So, and it will just keep on growing exponentially, getting higher and higher to astronomical numbers. So that's why you can kind of compare these. You can see this one's going to grow. It's going to start off slow, like you see. The exponential starts off slow, but then grows very quickly after not too much doublings or, so on. Quadratic one definitely grows more than linear. Linear is just a straight shot, you get what you get. 1 day, $1, 10 days, $10, 100 days, $100, and so on. All right, let's take a look at our last one, number 9. Now, number 9, again, we're just using the data here. It's a real-life situation problem, but really it is just looking at the data here and seeing is it a linear, exponential, or quadratic function. So again, using that data table, we're going up by ones here on the x. I'll go ahead and have you pause the video, try to see if you can figure out if this table with this situation about a ball being dropped, is this a linear model, an exponential model, or a quadratic model? So go ahead and pause the video and see if you can figure that out. All right, so let's take a look and see here. If we look at our differences from 305 to 289, we are going down there. So we are going down. How much are we going down? Well, it's 5, 15, 16. It looks like we're going down then. From 289 to 241, we're going down again. Let's see, we're going to be going down 50. So it looks like 50 on this one. Is it 50? So that'll be 90 to 41. Now you can always just check it. I'm trying to do my head, but I'm going quick, and minus 241, it's 48. So yeah, it's 48. I was thinking 50, but I went the wrong way with my 9 and my 1. That's right, there's 9 here and 9 in that one. Yep, that would be it. So 48, going down 48. And then from 241 to 161, let me just easier to make sure we see it here. 241 minus 161, going down again. We're going down 80 on that one. Going down 80. And then from the next two here, from 161 to 49. Oops, messed that up. 161 minus 49. There we go. 112. So definitely not linear. And we're not seeing exponential either because we're not multiplying by something to get the next one, not by the same thing anyways. So now let's take a look at our second differences just to see about the second differences. So from negative 16 to a negative 48, we're still going down here. So how much are we going down? So we take a difference here, say 48 minus 16, that is 32. So we're doing a negative 32 direction. From, we can say 80 minus 48 and see what that would be. 80 minus a 48. It's also 32, going in the negative direction. And right there, we can definitely see that's going to be also 32 in a negative direction. So definitely a quadratic function. So our answer here is that it is a quadratic. And the reason why is because second differences are constant. All right, so that's it for 8.6, and actually I finished off chapter 8 as well. So I'll see you again when we start chapter 9. Have a great rest of your day.